Okay, today we are going to talk about topic 3, which is going to cover piecewise and polynomial functions. So at this point, you should have a basic understanding of domain and range, intercepts, asymptotes, intervals of increase and decrease, intervals of positive and negative, and the transformations of functions. What you will learn in this lesson is what a piecewise function is, how domain and range affect a function, how polynomial functions behave. And so we'll look at end behavior, when a function is increasing and decreasing, and when a function is positive and negative. Okay, so piecewise defined function. What is a piecewise function? A piecewise function is a function that is broken into different pieces. The pieces are different equations. They could also be different types of function. So the functions cannot overlap, so they have a set domain where it becomes one piecewise function, and that function can exist. So a real world example of when you might see piecewise functions is costs of things. So our example says a psychic's fee is based on the length of time spent talking. So up to 5 minutes, that costs you $50. Over 5 minutes and up to 15 minutes costs $70. Over 15 minutes costs $70 plus 5 minutes per minute above 15 minutes. The time will be your input, and that's your x value, and the cost will be your y value, or your output, that f of x function. So one of the things I want you to note is it's saying up to 5 minutes, and it's wanting to know the length of time. So what is the lowest number of minutes we could be on here? Well, generally speaking, 0 is as low as you can go when you're talking about something like minutes, because minutes have to remain positive. But if you were equal at 0 minutes, then you were never on the phone with them. So it has to be greater than 0 minutes. That could mean 1 second or 2 seconds, okay? So let's look at this in a graph. Okay, so here is our function. And if you see over here, we have 3 different functions on here that are highlighted, and those are color coordinated. And so we have a constant equation here, a constant equation here, and then a linear equation here. And I know it's linear because it is forming that diagonal line. And so in that slide, I just talked about setting that number as 0. So if you were looking at this as a function, okay, remember this x value, this is our time spent. So if I spent negative 5 minutes, it cost me $50. And that mathematically doesn't make sense. And so you need to set that lower boundary. And at 0, we are not crossing that axis. So at 0 minutes, it cost me $0, or that line does not continue all the way to that function. Okay, so it is not always completely necessary to define that lower bound, but mathematically it makes sense in some situations where you're talking about a number that cannot become negative. So this is the same piecewise function we just looked at, but we're going to evaluate it. So how much would it cost for 12 minutes with the psychic? And so when you're evaluating functions, this tells you the x value, the minutes. That was our time, our x value. So I need to figure out which one of these 3 intervals that 12 can fit into. So is 12 less than 5? Is it greater than 5 but less than or equal to 15? Or is it greater than 15? For this situation, we are between 5 and 15. So that means it cost me $70 to talk on the phone for 12 minutes. This one says evaluate when x equals 20. So I need to determine which of these intervals that x value falls into. This last one, x greater than 15, 20 is greater than 15. Because this is a function, I now need to plug in that x value of 20. So 70 plus 5, parentheses, 20 minus 15. So if you simplify, 20 minus 15 gives you 5. 5 times 5 is 25, plus 70 gives you 95. So how to graph a piecewise function. Graphing a piecewise function is pretty simple if you know how to graph any type of function. So identify the boundary lines is going to be that key piece. So you can draw both of the equations and the functions as they are, and then go decide where those boundaries are set, and then erase the part of the graph on the side of the boundary line you don't want. And so this doesn't necessarily erase it, but you can visually see a little bit of how it's going to change when you set those boundaries. Okay, so for this activity, the piecewise function is defined by lines 2 and 3, and you can see that because these have the x intervals, what my x values can be. Okay, so first it wants us to look at lines 4 and 5, and so lines 4 and 5 are just those two functions graphed just as they are with no domain defined. Okay, but I can't overlap, right? This is supposed to combine into one singular function, and so for something to be a function, those x values cannot duplicate. So this part where they're overlapping would have to go away. And so that's whenever you set those boundary lines, okay? And so for this one, my boundary line is at x equals 0, and you can kind of see that purple line that's crossing right there. So that quadratic function, that's going to be that green function, it wants everything less than 0. So that's going to be to the left of this boundary line. So we're going to keep this piece of that function. Okay, so that means this side on the right side of that y-axis, that's going to disappear. And for that linear equation, it wants everything greater than 0 or equal to. So it's going to cross at that point, and it'll keep everything on the right side of that y-axis, all of those positive x values. So everything on the left of that y-axis for this linear equation will disappear. So I'll keep that boundary line there so you can kind of see. I know it's hard to tell the color. And then we can set that as our quadratic equation, and you can see it stops at that boundary line. And our linear equation, you can see it is starting at that boundary line. And so this is a function now because it can pass that vertical line test. That boundary line is not a real line, so it does not count. Okay, and if you zoom in on this, you can see a little bit better how close it is getting, but still not completely accurate. So how to evaluate a piecewise function. In general, you will be given a piecewise function set up something like this. So given the value to evaluate, so that's this number in parentheses, that -2 or this +6, identify which domain interval it falls in. Okay. Once you determine which interval it falls in, plug the value into that function. So this interval goes with this function, this interval goes with this function. So this wants f of -2. So is -2 less than -3, or is it greater than or equal to -3? This one is a little tricky to some of you. -2 is closer to 0 than -3 is, so it is technically greater than -3. So I'm going to take -2 and plug it into x squared. So -2 squared gives me 4. Evaluate f of 6. Is 6 less than -3 or greater than or equal to -3? What is greater than -3? So we're going to plug it into this function. So 6 squared is 36. So there are specific types of piecewise functions called step functions. And those step functions take those different pieces and they're becoming constant functions, meaning it's just a straight horizontal line, okay? And they increase, and that's why they look like steps and they're called steps. And so we have two different kinds. We have what's called a floor step function and a ceiling step function. And those terms, floor and ceiling, they just have to do with those intervals and those symbols, okay? So a floor function would include everything on the floor, right? So everything on the bottom. So this is the bottom of this interval. This is the bottom of this interval. So for floor functions, that is when that left interval or that left inequality symbol is equal to. It is including those lower bound numbers. For ceiling function, that upper interval is what is equal to. Ceiling, that's what's at the top, right? So what is at the ceiling of that function is what is included. Everything that is on the floor is not being included because it is that ceiling function. So we can look at this. So this is for the floor function. And so you can see those dots filled in on the bottom. That is the part that is included in the graph. And you can see it's forming those steps. Generally, these step functions, you'll see multiple, more than just 3. So there might be another step here and then here, and it will continue. And it will look just like steps. And since this is that floor function, that upper piece of that interval, right? Each of these lines is a different interval. This is my interval from -4 to -2. It's the x values between there, and then it stops. Okay, so those are the equations that you're looking at. Okay, that lower bound is what is equal to. Okay, now let's look at the ceiling. So those horizontal lines are in the same spot, but all that changed was those endpoints. So now we're on the ceiling function, meaning we want those upper bounds to be equal to. So you can see that right endpoint is filled in, and then the lower bounds are not equal to. So those lower endpoints are open circles. Okay, can you chill with the drinking? Please lay down. I'm busy. Go lay down. An absolute value function is a very famous piecewise function. Most people don't think of it in terms of it being a piecewise function. So this is a piecewise function because this part has a different equation than this part. Okay, so my boundaries are not always the same, and I do want to talk about this equal to, but this slope of this line is a 1-to-1 slope, but it is going in the negative direction. So this function is negative x. This function is going in the positive direction, so that function is positive x. When you are setting these bounds, you can't overlap. I can't have 2 of those bounds be equal at the same x value, because in general speaking, those y's would be different values. You do run into that exception when you are talking about the bound being a 0. This is not every single case, but in most cases, when those piecewise functions are overlapping at 0, the x is 0, and in most cases, the y is also 0. So whenever you create those points, it is still a unique x-y coordinate. Those y values are the same for both functions. So if I take this 0 and I plug it in here, -0 is just 0. So my x value was 0, and the y solution is also 0. And for the second part, if I plug in a 0, then it is y equals 0. So in both cases, I plugged in an x of 0, and in both cases, I got a y of 0. So that y value is still unique to those x values. So it can still be a function whenever that 0 is being overlapped, and it can be set equal to on both. You don't want to set both equal, so in general, you would pick one or the other. Usually, I pick the top one. Okay, I do have it set up this way just to show you there are some cases where it does not always matter. Now, if I were to shift this to the right a little bit, then I may pick the number 3, and so I might have something less than 3 and plug it in there, greater than 3, plug it in there. And if I were to plug in a 3 value, -3 and +3 are not going to be the same y value. So if I shift this graph any, then I can't keep those equal signs on both of those intervals. So this is a very special case whenever both functions are meeting at 0. Okay, so being able to write a piecewise function. So it gives you some specific information and it wants you to write the function. So you're going to write what the y values would be, or what the function or equation is, and then what the interval should be for that to be the case. So for the first one, it says children 5 years old and under are free. So that means anyone between the age of 0 and 5 is free. And when you're talking about age, you don't normally have to say a number like 0, but we don't have negative ages. So whenever you're talking about it in terms of the function, you do want to set that lower bound of 0, because it won't make sense in this context if you include those negative values. So then the next one is between 5 years and 12 years inclusive. So 5-year-olds are free. So in this scenario, the 5 years, I can't actually be 5 and be charged $10. I have to be a little bit older than 5. So I can be 5 and a day, 5 and 3 days, however you want to look at it. This inclusive, though, applies to the 12. So I'm between 5 and up to and equal to 12. So for the same thing for this next one, between 12 and 18 inclusive. So 12 was included in this one, so it cannot be equal to in this bottom one. 18 is inclusive, so it is equal to. So then adults, because 18 was included, adults would be strictly greater than 18. So here is what it looks like. So $0 if you're between the ages of 0, so a little bit greater than 0 years old, and up to 5 years old. So equal to 5, but not greater than. And for the next line, it's $10 if you are greater than 5 years old, but less than or equal to 12 years old. $25 if you are greater than 12, but less than or equal to 18. And $35 if you are older than 18 years old. Write a piecewise function. So we have a couple different piecewise functions that we're going to look at. So when you are writing these piecewise functions, what you want to look at is the equations of the lines. And one way you write equations of a linear function is that intercept. Okay, so wherever you're crossing that y-axis. In both of these cases, that y-intercept is 0, and that is where my functions are meeting. So for this equation, I do want to find out the slope. This looks like it is a positive slope of 1. I go up 1 over 1, up 1 over 1, and I'm crossing at 0. So this equation is just y equals x. And for this equation, my slope is up 2 over 1, up 2 over 1. So this equation is going to be 2x, okay? And so then we have to identify those boundary lines. And so for my boundary lines here, I want all of the values for this function that are less than 0. And you can say less than or equal to 0. And for this right bound function, I want all numbers that are greater than 0. And depending on which one you put the equal to sign on, just make sure at least one of them has it. For the second function, you'll want to extend these lines through this graph, through this y-axis, so that you can write the equation properly. So this looks like it has close to a slope of 1, probably as close as it can get. So if I were to continue this function, I would cross my y-axis at positive 2. So it's a slope of 1, y-intercept of 2, so that is x plus 2. For this function up here, that is crossing at positive 3, and it looks like it is also a slope of 1, so that's going to be x plus 3. For this function, we want to continue it down to the left a little bit, and that looks like it would cross the y-axis at at y equals positive 1. So my slope of this line is 1 to 1, so that is going to be a slope of 1 and a y-intercept of 1, so that's going to say x plus 1. So then you have to determine what those domain bounds are. So for that first equation, that x plus 2, that wants all of the x values less than, because it's towards the left, or equal to, because that circle is filled in, the negative 1. For this middle line, it wants the numbers between negative 1 and positive 1. And since those are open circles, we do not want to include the equal sign on those inequality symbols. And for my right bound function, I'm starting at positive 1, and I want all of the x values that are greater than that. So I want x greater than or equal to positive 1. So here you can look at it. This is the slope of 1, y-intercept of 0. This is the slope of 2, y-intercept of 0. I did set that equal sign on that upper function. And over here, this is that x plus 2 function, and I want everything less than or equal to negative 1 because I have that filled in circle. This is the x plus 3, and I want those to be open, so I do not include them as equal to. And this function was x plus 1, and it is a closed circle at positive 1, so we want equal to on this function. When you have a piecewise defined function, why can the intervals not overlap? And remember, the intervals are the x values or the domain. Now we're going to start talking about polynomial functions. Polynomial functions are able to be discussed more accurately when they're written in standard form, and that is one of the things that we've covered before. But just to review, standard form is when you write the function so that the highest exponent is first, and then you get smaller and smaller each time. So if your highest exponent is a 5, you would make that the first term, and then you would decrease. So 4, 3, 2, 1, and your constant term. Once it is in standard form, the coefficient of that leading term, that number in the front, that is called the leading coefficient. And the highest exponent in that function is called the degree. So there's a couple ways that you can discuss there are a couple ways you can identify polynomial functions. One of those ways is by the degree, or what is the highest exponent that is in that function. And we have 6 different degrees that we have specific names for. So we have constant, which is a degree of 0. So that means that there is no variable. If my degree is 0, that means the variable disappears. And then I have linear, which is a degree of 1. That means it is just an x term with no exponent. When you don't have the exponent written, remember we assume it is a 1. Quadratic, that is a degree of 2, so I have my highest exponent of 2. And then this is in standard form, so then my next exponent is a 1, and then this exponent is a 0. Cubic, that is an exponent of 3. I do not have an example over there. Quartic, exponent of 4. Quintic, exponent of 5. When you get into 6 and higher, you don't necessarily want to identify them by their degree, but you would start identifying them as the 6th degree or 7th degree polynomial. You can also identify it by the number of terms it has, so you can call it a monomial if it only has one piece. It's a binomial if it has 2 pieces. It's a trinomial if it has 3 pieces. And it is a polynomial if it is 1 or more. So a monomial, binomial, trinomial, all 3 of those are considered to be polynomials. But when you're identifying a function by the number of terms, you want the most specific. So if one of these 3 applies, that takes priority over just calling it a polynomial function. And when it's talking about number of terms, this right here, 3x squared, that is one term. Terms are separated by plus and minus symbols. So this has 1, 2, 3, 4 terms. Understanding end behavior. So end behavior is a concept that can be kind of confusing. So to describe end behavior, we use specific notation. So we use x with an arrow pointing towards infinity. And that just means as x becomes larger in the positive direction. And then x to the negative infinity means x becomes large in the negative direction. And we use the end behavior to describe what is happening on the ends of the graphs, where those arrows are going. So this relates a lot to quadrants. And so if you remember from topic 1, the first quadrant is that upper right quadrant, and then it goes in that counterclockwise C shape. So 1, 2, 3, 4. Each of these quadrants has a unique xy pairing. So these pair are positive x values, positive y values for any point in this top right quadrant. Any points in this top left quadrant would have negative x values, positive y values. Okay, so quadrant 3, that's negative x, negative y. Quadrant 4, that's going to be positive x values, negative y values. So which quadrant the ends point to tell you what the end behavior is. So if my arrow is pointing towards this top left quadrant, it's going to relate to the negative x, positive y. If it's pointing in this top right quadrant, that's going to relate in the positive x, positive y. Okay. I know this seems like it might be a lot of little things to be looking at, but just let me explain. So every polynomial function has two ends, right? We have a left end and a right end. And so these two left graphs that you can see, that says degree even. Okay, that means the highest exponent is an even number. And so one of the most common ones we've learned about is quadratic, right? That's that U-shaped graph. And so this graph could be continued to make that U shape. So it looks a little bit like it could form a quadratic. Same thing for this one, okay? And so from that previous slide, those quadrants and what those x and y values are, this top left quadrant, that's negative x, positive y values. And so when we want to relate it in terms of end behavior, this is as x is going to the negative infinity, y is going to positive infinity. And so for this right one, that's positive x, positive y. So as x is going towards positive infinity, y is going towards positive infinity. So you can relate what those quadrant values are to what those infinity symbols relate to, right? The negatives become negatives when you're talking about the direction and behavior of them. Okay, positive leading coefficient versus negative leading coefficient. So one of the things that you might notice on here is when it is positive, that far right arrow is pointing up. It's pointing in the positive y direction. And on these two, those y values are in the negative y direction. So that leading coefficient has to do with the y values at the end of the graph. Are my y values becoming positive or are my y values becoming negative? That tells me if my leading coefficient was positive or negative. This would be a really good table to keep in your notes. This non-bolded xy part, that is just in terms of the quadrant. All you need is this bolded part. As x goes to negative infinity, y goes to positive. X goes to positive infinity as y goes to positive infinity. And then I would include the degree and leading coefficient information as well as drawing this table out. So how to determine end behavior. So when you're looking at the equation of a graph, you can identify what graph might match it if you're looking at maybe a multiple choice question. And so that last slide kind of relates it to the pictures a little bit more, but the degree and the leading coefficient tell you what you need to know. So if your degree is even and your leading coefficient is positive, then both of the y's will be positive. If your degree is even and your leading coefficient is negative, then both of the y's will be negative. If your degree is odd, that means your endpoints are going to point in opposite directions. One will point up and the other will point down. Your leading coefficient is positive. That means for the lower interval, and all of these are written as the x goes to positive infinity, that's the right bound, that y value is positive. And you can see that positive y on that bottom one. So then degree is odd, leading coefficient of negative. So on that far right x bound, we want a negative y bound. Okay. So describe the end behavior. So it's just wanting you to explain what is happening as the x is going in this direction. So I'm going in the bottom left. That means I'm going left and down. So I want negative x values, negative y values. So this would be as x goes negative infinity, y goes negative infinity. One thing to note on this right arrow, it is in this top left quadrant, but if this graph were larger, eventually it would cross over into quadrant 1. So that is the positive x values, positive y values. So for this case, it would say as x goes to positive infinity, y goes to positive infinity. So in behavior on this one, they're both pointing up. Okay, on every function that we look at in behavior, we will have a negative y direction and a negative x direction and a positive x direction. So negative x going to the left is also going positive y up. Positive x going to the right is also going positive y up. So this is a different one. This is that left bound, right bound. As x goes negative, y goes positive. As x goes positive, y goes negative. And this is a even degree, and I know it's even because those arrows are pointing in the same direction. I know this one is odd because they're pointing in opposite directions. And so for this one, my end behavior as x is going to the left, y is going down. So as x goes negative, y goes negative. And as x is going right, y is going down. So as x goes positive, y goes negative. Identifying polynomial characteristics. So some of the things that we're going to look at is minimums and maximums, or the lowest points of functions and the highest points of functions. The interval of increase and the interval of decrease. And so the interval of increase, that's going to be, the interval is the x value. So between what x values does the graph look like it has a positive slope? So anytime it stops looking like it has a positive slope is where you would end that interval. And you can create multiple intervals for increase on functions. Interval of decrease, that's between what x values does the graph look like it has a negative slope. And the interval function is positive, is between what x values is the graph above the x-axis. And then what is the interval? The function is negative. That's between what x values is the graph below the x-axis. So above the x-axis, those are positive y values, which is why the function is positive. And below the x-axis, that is the negative y values and why the function is negative. So this is the first one that we're going to look at. One of the things that you can identify from looking at the graph is the degree. And so one of the things that we can note is are the endpoints going in the same direction or opposite directions? And so for this one, they're going in opposite directions. So I know that this is going to be odd. Hush. So one of the things that you can notice from looking at the graph of a function is what the degree is. And so if those arrows are pointing in opposite directions, then that is going to be an odd degree. And I can tell if my leading coefficient is positive or negative based on that right arrow. Which way is the graph going towards? So my right arrow is going up, so that is positive y value, so positive. It also wants to know minimum and maximum. Sometimes your graph will have multiple minimums and maximums. Sometimes it just has one. And there are two different ways that you can write these. And so minimum, that's the lowest point that we can see. And so this does have a line going down in the y direction forever. And so there is no specific minimum, but we have what's called local minimums, or minimums that you can see on the function. So this local minimum is at the y value of -2. So you can write it as y equals -2. or you can write it as whatever that point is. So that point is at -2, -2. And then for my maximum, again, I have this arrow pointing up, so I have higher y values. So we want to just look for that local maximum. And my max y value that I can see is that 2, so y equals +2. And I can write it also as whatever the coordinate of that point is. So that's the point -4, +2. Okay, so another thing we want to look at is what interval is it increasing on? And so increasing is where you're able to look at the graph and see where it might have a positive slope. And so if I'm tracing this with my pencil, then it looks like this part of that graph right here has that positive slope. So from here to it looks like about that point. Okay, and so this is an arrow on the end. And so when we want these intervals, we want to know the lower bound and the upper bound. So what's the lowest number it goes to in that direction, and then the highest number it goes to in the other direction. That arrow means infinity, and if it's an arrow to the left, that's a negative infinity. Okay, it's down and to the left if it is in this quadrant. Up to the left if it is in this one, up to the right, down to the right. Okay, so that is increasing starting at negative infinity, and we want to make sure we're putting parentheses with the infinity symbols. And we are increasing until we reach -4 on the x-axis. We do not care about the y values. We want to know between what x values am I increasing, okay? But if I keep tracing this function, I can see I start increasing again right here. So at -2, and I continue increasing with an up arrow. So from -2, that arrow is up and to the right, so that's positive infinity. So if you notice, I didn't use a square bracket on this -4 or -2. Those endpoints are called turning points. Okay, let me erase this. So this point right here is called a turning point. This right here is called a turning point. So if you recall from topic 2, I had you guys add minimum and maximum and turning points to that. And so those minimum maximums, those are occurring at those turning points. And so at this specific point, that point -2, -2, if I were to just draw a line, it would be a straight horizontal line going through that point. And so I'm not creating that positive slope or that negative slope. It's a constant slope, right? Just going straight across here. Anywhere else on here, I could draw it if I'm coming over here, right? That can be positive. But to go through that exact point one time, it's called a tangent line. You'll learn more about that in like trigonometry or some higher level math. But to create that tangent point, we want to cross it one time. And so any of those turning points, that tangent line is a constant. So it's not positive or negative at that point. So those endpoints on the increasing and decreasing, those cannot be included. Okay. So for my decreasing, I am between these 2 points right here. So this has a negative slope on the graph right here. So between -4 and -2, those x values. So -4 to -2. One of the ways that you can check yourself is this is a function that has a domain of all real numbers. That means I should use every single x value between -infinity and positive infinity. And so if you look, I have this interval, but I skip a chunk, and I skip the chunk -4, -2 before I continue on to that second piece. So these 3 combined does give me the entire x intervals. Okay. The next thing we want to look at is where we are positive and negative. Okay, so we are positive when we are above that y-axis. the x-axis. So we are positive, let's do a different color. We are positive right here, and we are positive starting right here, and then we've got that arrow. Okay, and so one of the things that we've talked about is the number 0. 0 is neither positive nor negative, so whenever I am on that axis, I cannot include that y value. So that y value of 0, or that x value of close to -5 cannot be included. So these are not exact cross points, so we will use an estimate. So I will just say that this point is at -5, and it stays positive until it reaches -3 right here. And then I have that second interval, and it starts, it looks like close to -1, and then it's going right forever. So I'm going to continue to the positive infinity direction for my x values. Okay, so then it wants the negative. So then we're negative where we are below the x-axis, so this interval and this interval. So that first one, that left bound is starting with an arrow, so that means infinity, and it is left, so negative infinity. And I am negative until I reach the x value of -5, that where that positive interval starts. And then I am negative again, starting at -3, continuing until I get back to -1. Okay. So this one is still, let's change color. Okay, so for this function, the first thing we want to discuss is degree. And so what is the degree of the function? Is it even or is it odd? Remember, even degree, the endpoints are pointing either both going up or both going down. And in odd degree functions, they're going in opposite directions. So one goes up while the other goes down. These are pointing in opposite directions, so my degree is odd. To determine the leading coefficient, you want to look at the right arrow. And so that right arrow, is it giving me negative y values or positive y values? And that tells me whether or not that leading coefficient is positive or negative. It's going down, so that is negative y value, so my leading coefficient in this case is negative. This wants us to identify our minimum values. And so we have an arrow pointing down, so we technically do not have a specific minimum, so we can look at that local minimum, or the minimum we can see. And that local minimum is at a y value of -7, so y equals -7. Or I can use that point. It's the point -3, -7. Either of these are acceptable. The key part to remember is it's talking about the minimum y value or the maximum y value. So make sure you're looking at that y piece, including those y values. So for maximum, it's going to be this, which is about 2.5. So y equals 2.5. And I can also write it as the point. It looks like about 1/2 and 2.5. So we're going to go 1/2 and 2.5. Okay, so I accidentally erased the degree, leading coefficient, minimum, and maximum. And so what I want to look at now is where I am increasing. And so if I trace this, I'm going down, 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 and then starting at this x value of -3, I begin increasing. And I increase until I reach that x value of 1/2, or negative 1/2. So that maximum was -1/2 and 2/2, and not +1/2. That is the only interval. It is going up, so that is my only increasing interval. So next I can look at my decreasing interval. And so that is starting up here. We are decreasing or going down until we reach this x value. So I'm decreasing starting all the way to the left, which is -infinity, until I reach that x value of -3. And then this part begins increasing. That's the interval we have above. And then starting at that -1/2, we begin decreasing all the way to the x value of infinity. So from -1/2 to +infinity, I am decreasing. Okay. So then we want our positive and negative intervals. So positive interval, that's going to be where I'm above the x-axis. So here I'm above, and it looks like here I am above. Okay, so I have two different positive intervals. That first one starting all the way at the left, that's at -infinity. And I am positive until I reach that x value of -4. And again, starting at, we're just going to say this is about -1 to about +1/2. And then we are negative, starting at about -4, and we stay negative until we get back to that x value of -1. And then we have another interval starting at about 1/2, continuing all the way to the right in that positive infinity direction. So 1/2 is that starting x value, and we continue to the positive infinity direction for the x value. Okay, so for degree, they're pointing in the same direction. That means you're going to have an even degree. Leading coefficient, that right arrow is going up. That is a positive leading coefficient. Your minimum, we're going to have two local minimums. So those are at about -1/2 and about -4/2. And then for my maximum, I only have one, and it looks like it's at about +1. Increasing, that's where I'm going up. So starting at about -1/2 till I get to 0, I'm increasing. And then starting at about 1/2 until I reach positive infinity, I am increasing. And I am decreasing starting the left -infinity until I reach that about -1/2. And I am decreasing again starting at 0 until I reach about +1/2. Or my function is positive and negative. I have three positive intervals. So my first interval is this line right here. So from this endpoint -infinity to about -2, I'm positive. And then I'm positive again starting at about -1 to about +1/2. and then again at positive 2, and I continue staying positive in the infinite direction. So positive 2 to positive infinity. And then where I am negative, where I'm below that x-axis, so starting at about 2 to about negative 1/2. And then starting at about 1/2 to positive 2, I am also negative. So this has two different intervals. Identify the following characteristics from this graph. Please rate your understanding of each of the following on a scale of 1 to 5. So 5 means you have a full understanding of that concept, and 1 means that you need some one-on-one help. So the first one is piecewise functions, minimum and maximum, increasing and decreasing, positive and negative, and end behavior.